My talk today is about the work we are doing in Project Oak, and specifically how we think about using attestation measurement in a way that supports open and easy external code reviews. I will cover three main areas. I will start with a brief overview of Project Oak and our current focus. This provides a motivating use case for external review. Next, I will go into more detail about the measurement of the workloads, specifically focusing on AMD SEV-SNP, which is the platform we are currently using. I will then explain our approach to help enable and support external code review and audits. So, starting with Project Oak. We are an open source research project. We aim to allow data owners to reason about how their data will be processed before sharing the data with the service. We focus specifically on the scenarios where the data owner is an end user. This is very different from the typical cloud-based confidential computing scenario, where the data owner is often also the owner of the workload image. They know what image is used to boot their VM and can usually log in interactively to confirm that things look as expected. This is not the case for an end user that uses a personal device to connect to a remotely hosted service. It's not feasible for every single end user to make an informed decision on whether or not a server will behave appropriately. Our approach is to rely on delegation of trust. We want to support an ecosystem of trusted experts and key opinion formers that can review the applications and give opinions on whether the user data is processed appropriately for the use case. Users can then decide which of these experts they want to trust or delegate their trust to. Our solution is based on a few building blocks. These are the three main ones that are relevant to this talk. We use a trusted execution environment, specifically AMD SEV-SNP. This provides two important features. Firstly, it acts as a reverse sandbox, protecting the workload from everything outside the trust boundary. This is important to be able to reason about the code running inside the trust boundary, since it removes the external influences. It also provides primitives for measuring the workload. We believe that normal sandboxing is also a useful tool for reasoning about workload behavior. If a workload is severely constrained, it could reduce the scope of potential risks that must be included in a review or an audit. We have built a very minimal microkernel, which we call the Oak restricted kernel. It acts as a very restrictive sandbox environment for our application. This is not intended to be a general-purpose operating system and provides very limited functionality. Transparency is another important building block. Our project uses open source code so that the code can be found by anyone. We also use append-only transparency logs to provide an uneditable audit log of things we publish, such as the released versions of binaries, claims about the properties of these binaries, etc. This audit log will provide public evidence of any potentially malicious behavior by application developers to enable detection by external experts. For this to be meaningful, the client application has to confirm that all the relevant artifacts it receives were published in a transparency log as part of its validation. At a high level, an Oak application is split into two parts. This is the trusted part, or there is the trusted part that runs inside the TEE and an untrusted part that runs on the outside. These two parts communicate over a single, very simple communication channel. All the complex logic that does not have to be trusted is moved outside. The untrusted launcher is responsible for launching the TEE, handling user requests, communicating with external services, etc. Only the pieces of code that must really be trusted are left inside the trust boundary. This could include things like cryptographic code or any code that must operate on unencrypted user data. The client can connect to the untrusted launcher instance and ask for evidence about the state of the trusted application. The client application can then evaluate the evidence and decide whether to share the data with the application or not based on this evidence. The data is encrypted so that it can only be decrypted inside the trusted application. For this to be meaningful, it must be possible to know that the application will do with the data exactly what is expected. Open source code is a good starting point, but to be really sure what the code will do, we also need to know exactly which version of the code is actually running inside the TEE. That is where the measurement comes in. As I mentioned before, we believe that users will delegate trust to experts and key opinion formers. The simplest way to implement this delegation is to do it out of band. This approach would be similar to current vulnerability research. Reviews will happen asynchronously, and if issues are found with the application, external mechanisms such as blog posts and vulnerability databases can be used to raise awareness of these issues. We are also exploring the idea of allowing the reviews to happen before launching a new version. In this case, each of the experts would sign a digital statement that they believe the new version of the application behaves appropriately. These signed statements can then be included in the evidence that is sent to the client application to help with the decision on whether the application is trustworthy or not. There are three main components running inside the trusted execution environment. The first component we call stage 0. It is a minimal virtual BIOS and bootloader combination that does the absolute minimum needed to get the CPU from its initial state to the point where the kernel can start running. When a new VM boots, the vCPU is running in 16-bit real mode and starts from a well-known instruction pointer. Our kernel provides a 64-bit entry point, so stage 0 must set up the structures, such as the initial page tables and the appropriate control registers, to allow the 64-bit code to run. It is marked with a dashed outline in this diagram to indicate its temporary nature. As soon as the kernel starts running, stage 0 goes away. When the kernel is booted, it replaces the initial page tables with its own new ones to make sure everything is correctly set up and that the stage 0 code is no longer executable. It also sets up some shared memory with the hypervisor to support the communications channel. The kernel is responsible for loading and measuring the application. It provides a very minimal syscall interface to the application. The application at the moment can basically only read from or write to a communication channel, ask for more memory, or exit. The kernel will also provide cryptographic services in future so that the application can ask for data to be signed or derive Diffie-Hellman keys. And finally, there is the application that implements the trusted business logic. As I mentioned before, its behavior is severely constrained by the restricted kernel. We currently only support a single application running in a single user space process on a single vCPU. We also don't support preemptive multi-threading. Next, I want to go into a bit more detail about measuring the workload. The main goal of workload measurement is to enable us to provide evidence to clients about the identity of the workload. To be able to reason about what an application does, we need to know which application is actually running. At the moment, we use AMD SEV-SNP as a trusted execution environment, so I think it is useful to discuss the measurement process. When a VMM wants to launch a new VM, it starts by allocating some guest memory for this VM. It then writes some content to this guest memory. In our case, this is the stage 0 and OC restricted kernel binaries. The VMM then notifies the platform secure processor, or PSP, of the modified pages. The PSP measures these pages and encrypts them so that they become readable from within the encrypted virtual machine. Once this is done, the VMM asks the PSP to finalize the VM in preparation for launching it. The PSP injects some special pages at this point, such as the secrets page, and then finalizes the measurement. It returns a measurement to the VMM, which the VMM can then use to check whether the memory was loaded as expected. If everything is in order, the VMM can start the VM. This means that the measurement is done once, and it happens before a single instruction has been executed on the VM. The VM guest can request an attestation report from the PSP. The attestation report contains important information about the state of the platform and the identity of the workload. Specifically, it contains platform configuration information, such as the current version of the SEV-SNP components, whether debugging or hyperthreading is enabled, etc. It also includes the measurement of the initial VM memory and the vCPU state. The guest can also provide up to 64 bytes of arbitrary data to be included in this report. This is typically used to bind a public key to the attestation report. In our case, we use it to bind a key that the kernel can use to endorse data, such as the measurement of the actual application. The report is signed using a hardware key that is unique per machine and depends on the versions of the SEV-SNP components currently running. It is called a version chip endorsement key, and the certificate chain that proves the validity of this key can be downloaded from AMD servers using a hardware ID of the machine and the version information. As I mentioned before, stage 0 and the kernel are loaded into the initial VM memory before booting. So these are both covered by the initial measurement by the PSP. The application is loaded later, so the kernel is responsible for measuring it before launching it. The kernel does not have access to a file system, so it receives the application binary over the communications channel from the untrusted launcher. To allow the client application to make trustworthy decisions on whether a specific application instance is trustworthy, we have to provide it with the appropriate evidence. This includes the attestation report. The measurement in the report indicates which versions of the kernel in stage 0 were loaded. It also provides evidence of the validity of the key that the kernel uses to sign the application measurement. It in effect becomes a non-standard format for a certificate for this key. We also send a certificate chain that can be used to verify the hardware signature of the report to avoid the need for every client device to download it from AMD servers. Next, we send the signed application measurement and any other signed claims. These additional signed claims could include claims that are signed by the developer about the properties provided by the application, or claims signed by external reviewers that they believe the current version of the application processes data in an appropriate way. We expect that the client application will already have access to the appropriate certificates to validate the signatures on these claims. We also send inclusion proofs for all artifacts that must be published to a transparency log, to avoid the need for clients to interactively connect to the logs. This allows the client application to ensure that everything was published correctly without overloading the logs with client traffic or adding additional potential points of failure to the communication of the application. Lastly, I would like to talk about external reviews. As already mentioned, we believe that open and easy external review are important for allowing end users to meaningfully delegate trust decisions about what data they are willing to share with an application. We want to enable any person with the appropriate knowledge to be able to review the exact versions of all code that is running in the TEE in a reasonable amount of time, perhaps a couple of weeks for a detailed audit. This is a challenging goal. Since the measurement is a single hash, we must provide a way for the external reviewers to translate that into the exact source code that was used to generate the binaries that resulted in that measurement. In the more typical remote attestation scenarios, such as managing a fleet of IoT devices, the owner of the fleet already knows which hashes represent a good state of the device. In our case, we want to rely on an ecosystem of reviewers to effectively maintain such a list of known good hashes. There is also the time of check versus time of use problem. The measurement happens before the VM starts booting. How can we ensure that we know what code is executing an hour later, or perhaps even a day later? This is especially problematic in VM-based trusted execution environments that are focused on supporting general-purpose operating systems and arbitrary workloads. These typically need to start and stop processes, etc. Lastly, detailed code reviews and audits are time-consuming, complex, and expensive. If we want to eventually build an active and diverse ecosystem of reviewers, we have to help them to make this as easy as possible. To enable the translation of measurement hash to expected source code versions, we publish some breadcrumbs during the development and release processes. These breadcrumbs can then be used later to do a reverse lookup to trace the path back to the source code that resulted in them. Every time we merge a new commit in our repository, we automatically publish provenance information as part of our CI pipeline. This includes the hash of the resulting binary, the repository address, the exact source code commit, the builder, which in our case is usually a Docker image hash, and the command that was used to build the binary. Since our builds are reproducible, an external reviewer can fetch the source code, the Docker image, and execute the build command and check that the resulting binary has the same hash as specified in the provenance information. When we release a new combined version of the kernel in stage 0, we will publish an expected measurement based on the two binaries, together with the hashes of each of the two binaries. When releasing a new version of the enclave application, we will also publish the expected hash of that application. Later, when a reviewer wants to map the measurement back to source code, they can search for the attestation measurement. That will then provide the hashes of the stage 0 and kernel binaries that would produce those measurements, or that measurement. They could then look up the provenance information from these hashes to find the source code that was used to build these binaries. They can validate both using reproducible builds. We also provide an open source tool to recalculate the expected measurement from these two binaries. So the researcher can use this tool to validate that the expected measurement resulted from these newly built binaries. Since the application measurement is a single hash of the application binary, the researcher can directly find the provenance information from this and use a reproducible build to validate that it was built from a specific source code commit. To address the time of check versus time of use issue, we rely on the restricted kernel. As soon as the restricted kernel boots, it marks all of its executable memory as read-only. There is no facility to change the executable memory back to being editable. The kernel creates a single process and loads the application into it. It marks the executable memory of the process also read-only. There is no mechanism for the application to mark the executable memory as editable or to mark any other memory as executable. This means that the executable memory will not change over time. We also only generate one attestation report. It is generated before the application is started. The application can request a copy, but it cannot generate a new report. This is to prevent the application from creating a spoofed endorsement key, for example. Since the report is signed by the hardware, any tampering will be detectable. To make code audits easier, we use a few different techniques. By having a minimal kernel and moving as much of the complex logic as possible outside of the TEE, we reduce the amount of code that needs to be reviewed. The kernel, stage 0, and the application can be released independently. So if one of the components are updated, the others do not have to be re-reviewed. The code for the restricted kernel in stage 0 should remain quite stable. We also believe that the restrictive sandbox execution environment provided by the kernel makes it easier to reason about the code being reviewed, as it limits the many potential attack surfaces and also limits the features of the application. We have also recently started providing some hints to help reviewers. The idea is to add properties and invariants we expect from various components to the documentation in the repository. We also include code pointers to where these properties or invariants are implemented. We plan on expanding this to cover much more of our code base in future. This will hopefully help ease the exploration of the code base for any reviewers that are new to it. While I hope all of this sounds like a good idea, it is important to point out that this is not appropriate for all scenarios. Redesigning and re-implementing applications to match this restrictive execution model with the split between trusted and untrusted pods can be complex and time-consuming. The threat model for a specific application should be used as the basis for deciding whether this additional cost is warranted. Another point to note is that the trusted execution environment cannot defend against all possible attacks. So it's important to understand the threat model for an application and consider adding additional software defenses if needed. An example could be implementing something like oblivious RAM if there is a concern about leakage through memory access patterns. To summarize, we want to make it possible for any data owners, including end users, to be able to reason about how their data will be used. The ability for anyone to do external code reviews is important to support this vision, and we are working to make it as easy as possible. Knowing exactly what code is running is a prerequisite for meaningful review, and we use the attestation measurements to help with that. Thank you for listening. If anyone is interested in connecting with us, there is a link to our Slack channel at the bottom of the homepage of our GitHub repo. Thank you.